Okay, hi everyone. Welcome back to GOCC. Today we have Madeline Brandt from Vanderbilt talking about the topology of tropical moduli spaces. Before we get started, let's just recall our community statement. We are all learning, everyone has something to contribute, and no one has all the answers. So Madeline, whenever you're ready, go ahead.
Thanks for the introduction, and thanks for inviting me as well. And I also really like your community statement. And yeah, I just wanted to add, like, uh, I don't know what y'all's backgrounds are, and so if anyone has any questions at any point, feel free to just stop me. I would like much prefer that you come away from the talk having learned something than for me to like get through all of the slides. So yeah, feel free to yeah, just ask any questions. So today I'm gonna speak about the topology of tropical moduli spaces. And I'm actually, oh, okay. And so I'm going to try and give sort of like an overview of like a recent trend in tropical geometry or combinatorial algebraic geometry, which has been to try and say something about the cohomology of a moduli space by looking at the corresponding tropical moduli space. And so yeah, so what I'm going to do is sort of like give an overview of that idea, and then if there's time later on, then I'll talk about like a specific project that I did looking at using those techniques. So uh, the two sort of main characters in this talk, and the two like main cartoons to keep in mind are going to be this picture and this picture. So these are both instances of moduli spaces, and I'll sort of like give you an idea of what that is. But this is like more of a classical one, and this is a tropical one. And so in this talk, I'll say like how to construct these two examples, and then also how they're related. And so the main ideas are that classical and tropical moduli spaces are connected. So there's going to be some sort of way to pass between these two objects. And in fact, the tropical space does say something about the classical moduli space. So that's sort of the second point, which is that we can use this connection to understand the cohomology of the classical moduli space via combinatorics, which comes from the tropical moduli space on the right-hand side. Okay, so let me just start by saying like, what is a moduli space? So very broadly, like mathematicians are interested in classification problems. So if you have some class of objects and a notion of what it means for two of those objects to be equivalent, a natural question is, when are two such objects the same? How do you detect whether or not one is equal to another one? And moreover, like how do you describe all equivalence classes of your objects? And moduli spaces offer sort of a geometric answer to this question in the case when you have a geometric classification problem. So the idea is to make a space whose points actually correspond to equivalence classes of the objects. So you can think of your moduli space as kind of being some menu where you like point to a specific point in the space, and then it conjures up some object that you're interested in, or an equivalence class of the objects that you're interested in. And in algebraic geometry, typically, a nice feature about this is that as you move this point around in your space, the objects, like nearby points, correspond to objects that are similar to each other in some way. So the maybe the familiar example is of P1. So P1C classifies lines through the origin in the complex plane. So over here, I have sort of a cartoon of how it might look. So there's like a point that I've labeled 0 that corresponds to a line with slope 0 in the complex plane. And then going around this direction, the line gets steeper and steeper, positive slope. And then going around in this direction, it gets steeper and steeper, negative slope. And over here, they meet up when you have a vertical line through the origin. And so some key features about this in terms of thinking about it as a moduli space is that every point in this space communicates some line to you. So like our classification problem is lines through the origin in C2. And so yeah, every point corresponds to some line through the origin. Every line here is represented exactly once. And furthermore, this sort of space captures how lines vary in families. So if I move around continuously inside of this P1, then that also will like continuously change the slope of the line. Maybe I'll pause for a second and see if anyone has questions. We're good. Okay. I think I can only see like a subset of the people, but everyone who was visible gave me like a thumbs up or a nod. So I'll continue. Okay, so here's like the second example. So I'm going to look at so-called n-marked P1s. And so here's what our objects are going to be. The object is going to be an n marking of P1, which is a choice of ordered n tuples of distinct points on the P1. And there's sort of two cartoons that I'll use to depict P1 in this talk. So to an algebraic geometer, P1 is a genus 0 algebraic curve, and it's actually the unique genus 0 algebraic curve. So usually you just draw it as a line. But a geometer might say that this is actually the Riemann sphere and draw it as a blob. And I will use both of these cartoons just depending on sort of like which one is better for gaining intuition for the specific situation that I'm in. But yeah, just know that this is sort of like two different drawings that I'll use for P1. So yeah, back to the n marking. So here's one n marking, one 4 marking of a P1. So I have like one point labeled 1, another point labeled 3, one labeled 2, and one labeled 4. So that's my 4 tuple of distinct points. And then here's like another sort of depiction. Okay, so those are my objects. And then I also need a notion of what it means for two objects to be equivalent. So I'll say that one n-marked P1 is equivalent to another one if there is an automorphism of P1, so just an element of PGL2C that carries the one n tuple to the other n tuple. Okay, so that's when two are equivalent. And there's like a key fact, which is sort of like a homework exercise. But if I give you 3, so if you have your favorite 3 points on P1 and I have my favorite 3 points on P1, then there's actually a unique automorphism taking the P sub i's to the Q sub i's. So the sort of like conventional favorite choice of points is 0, 1, and infinity. So yeah, given any 3 points, I can always find some automorphism that takes those 3 points to 0, 1, and infinity. Okay, so then it is a theorem that there is a moduli space of such objects, and we'll construct the first few examples, but I'm just going to let M0n denote the moduli space of n-marked P1s. So let's look at what this is for n equals 3. So by the fact from the previous slide, M03 is just a point, because if I have any 3 marked P1, the fact tells me that it's equivalent to my favorite one, which is the one marked 0, 1, and infinity. So there's actually only one equivalence class of 3 marked P1. And then for n equals 4, So again, by the fact, I can start by assuming that the first 3 points are 0, 1, and infinity. And then my choice of P4 can then just be, so the points have to be distinct. So P4 can be anything from P1 minus those 3 points. And so that means that the moduli space is actually just P1 minus those 3 points. So here's like my cartoon of how this looks. So I'm not allowed to pick 0, 1, or infinity. So as I drift this point around in the moduli space, the 4 marked P1 that it corresponds to is the one where that point is selected as P4, my fourth point. Are there questions?
So you said that when you move the point around, you get different corresponding spaces.
Yeah.
So like if you jump over the zero, do you get like a
Yeah, okay, yeah. So this is like a key issue. So there right, M04 is not compact, right? So what happens is I start to take a limit of that point as it goes towards like 0, say. So that I'll address that question in like
okay.
2 slides. Yeah. But that is,
Okay.
yeah, the key observation. Yeah. Other questions? Okay, so then I'm also gonna do n equals 5 just for fun. So basically here we're now gonna have a choice of fourth point and a choice of fifth point. And the fourth point cannot be 0, 1, or infinity. And then also the fifth point cannot be 0, 1, or infinity. And lastly, the fourth point and the fifth point cannot equal each other. So how the space looks is we have like a P1 times P1, where along one axis I have like my choice of what P4 should be, and the other axis has the choice of P5. And then there's all these gray lines sort of depicting the like illegal hyperplanes where I cannot select those 2 points. So my example here is like I've picked P4 to be, okay, so like obviously this is a cartoon, but like in the cartoon it's to the right of infinity and P5 is to the left of 0. So of course like that's to the left and to the right doesn't really make sense, but yeah, so just in the cartoon, that's sort of like how it would look. Okay, so that's M05, and you can keep going in this way to construct M0n for larger n. Okay, so as we were just remarking, M0n is not compact for n greater than 3. So the problem is we can't take limits, right? So if I have a 4 marked P1 and I start sort of sending the fourth point towards 0, there's nothing right now in our space that's in that limit. So the key insight of Deligne, Mumford, and Knudsen in 1969 was that we should, instead of just looking at n-marked P1s, we should sort of like slightly broaden the class of objects that we're looking at so that our moduli space is compact. So, and you're just adding in some stuff into the boundary, basically. So what gets added? So previously, P1 is just from the perspective of an algebraic geometer, it's a genus 0 curve. So now I'm going to allow nodal genus 0 curves. And so that's just like allowing for like the mildest possible singularities. Like it doesn't have like a cusp or anything wacky. It's just nodes are allowed. And then I need to select n distinct smooth points on that nodal curve. And then the last thing is that it has this, there's this stability condition, which is that you ask that the curve has finitely many automorphisms. And this is sort of just like a technical assumption, which will ensure that the moduli space comes out having sort of nice properties. So here's like an example of a 6 marked nodal genus 0 curve. So how you should think about this picture is that like each of these like sticks corresponds to a P1. And when they meet in an X, that's like a node. And then these blue points are my marked points. And the stability condition is equivalent to just asking that every stick has like 3 special points. So either a marked point or a node. Okay, so that's like an example of something that's been added to the space.
Yeah. I have one little question. Those three roughly horizontal lines,
Yeah.
do any two of them have a point in common?
No.
Okay.
Yeah.
Okay, thanks.
Yeah. Are there other questions? Okay, so how does this solve our problem? So actually, like, what should replace the question mark here if P4 drifts towards 0? So what happens is when P4 drifts towards 0, instead of having them be equal to each other, because we still have to select distinct points, they now just quote unquote sprout off onto a new component. So for someone who does have algebraic geometry background, the way that you should think about this is that you blow up the point where they collide and then record like the speed at which they collided with each other. So that's sort of like what this is like representing. So here's how the picture looks now. So here's I'm going to call this compactification M04 bar. So we previously had 3 holes right here. And now we've filled in the holes with, for example, this picture where P4 and 0 coincided. We branched those off onto a new component. When P4 hits 1, then they sprout off onto a component together. And then when P4 and infinity collide, they sprout off onto a new component. So this is like the picture of like how the space looks compactified and sort of what those boundary components that we've filled in, what they are parameterizing. Okay, so now I'm going to sort of switch gears. So that was like, if you have a distaste for algebraic geometry, now I'm going to go in like a purely combinatorial direction. So we can also create moduli spaces that parameterize combinatorial objects. And for the purposes of this example, here's the combinatorial objects that I'm going to be interested in. So my objects are going to be genus 0 n-marked tropical curves. So what is this? It's going to be a graph that has no cycles, so it's a tree and it's connected. I'm going to put n labels on the leaves. Every vertex has to be at least trivalent. And it's also going to be a metric graph, so the edges will have some lengths. And if you sum across all edge lengths in the graph, then I'm going to restrict the total to be 1. Okay, so this is like a lot of random conditions. It's not clear where they came from, but the point is like, this is going to be like the object, the correct like moduli space to compare with the algebraic geometry example that we've been looking at. Okay, so when are 2 such things equivalent? So if you have a graph isomorphism that preserves the labels on the leaves, then that will be when 2 of these things are equivalent. So here's an example of like what they all look like for n equals 4. So since I have the total interior edge length has to equal 1, that means that I actually do need some interior edges in my tree. And then the tree has to have 4 leaves. And so these are, and the leaves are labeled 1 through 4. So these are the like 3 distinct options that you get. Maybe I'll pause and see if there's questions.
Oh, I have a question.
Yeah.
So say the total is 1. Does that mean that if you sum up the lengths of the edges, you get 1?
Yes, exactly.
Oh,
Yeah.
so the blue edges would be 0, length 0?
Yeah, the leaf edges,
You,
yes, these like light blue ones, you just consider those to have length 0.
so you could have like an eighth for the blue ones and a half for the black one.
No, the blue ones just always like the leaves don't contribute to the total length.
Oh,
Yeah, it's just the internal
okay.
edges. Yeah, yeah, yeah.
Oh, okay. Okay. So that's okay. Thanks.
Yeah. Are there other questions?
Is the edge length somehow encoding this like speed at which points are colliding? Or what is,
Yeah,
okay.
yeah, yeah, exactly. Yeah. Are there other questions? Okay, so I'm gonna denote by M0 trop the moduli space of these objects, so genus 0 and marked tropical curves. And here's how the space looks. So from the example on the previous slide, there's just these 3 options. And so this space, the moduli space of these things is just consists of 3 points. And here's how M05 trop looks. So it's actually sort of looks like a Peterson graph. And so let me just like go into this a little bit. So the vertices correspond to the trees where you only have 1 internal edge and you have 3 of the leaves on one side and 2 of the leaves on the other side. And I've suggestively named the leaves 0, 1, infinity, P4, and P5. But anyway, so those are the vertices. And then the edges come when you start to drift one of the leaves across the internal edge. So here we have like the leaf called infinity is sitting now in the middle here. And when it's closer this way, this edge would have smaller length. And as it goes that way, this edge grows and this edge shrinks. So that's sort of like how this space looks. And yeah, this is again like you could if you wanted to, you could sit down and write down all of these trees and like how they link up, and you would see that you get this like Peterson graph out of it. Okay, so yeah, how are these 2 spaces related? So there's sort of this like dualization process. So let's say I take one of these things that is sitting in the boundary. So if I have an n marked curve, there's a way to associate to it an n marked dual graph. So I take the components, so like these 2 blue components, and those will become vertices of my graph. And then wherever I have a node between 2 components, that's going to make an edge in the graph. And then these markings will turn into leaves in the graph. And so this is like a way to take, one of these like stick drawings and get a graph out of it. And so what happens is this compactified M0n, this is actually stratified by dual graphs. So what that means is that M0n bar breaks up into these smaller pieces, M sub t, where M sub t consists of all stable curves whose dual graph has a specific type. So here's like how the picture looks. So if I look at like the part, the interiors, right? So the part that we didn't fill in, that would just be a P1 with no nodes and 4 marked points on it. And so the dual graph would look like this. But then if I say, okay, whose dual graph looks like, here we have one component with 1 and P4 on it, and another component with 0 and infinity. So this would look something like this. Right, so then that gives me one piece of my moduli space. So yeah, so looking at the tropical moduli space, that will tell you what like all of the points in your compactified M0n bar looked like. And so one thing you can, oh yeah, do you have a question?
So for the type for the blue one, uh,
Yeah. Oh,
that has length 0, right? The total, because it only has
yeah.
leaves, or
Yeah. So yeah, let me go back to this picture really quick. So if you don't restrict the edge length to be 0, then this edge length can vary, right? So each of these would give you a ray. So your space would look something like that. And then that tree that has no internal edge, just one vertex and all the leaves sitting there, is the point in the middle of this. And the sort of like difference between these two perspectives is that to take the picture that's currently there and recover the one that I had, you just take the link of this space, so like intersect it with a sphere. And conversely, if I want to get the picture that I was just drawing you, then I would just take the cone over the picture that is currently on the screen to get back the 3 rays. So yeah, so what do I want to say? Like, you can deal with either of those two pictures, I guess, and you'll be able to recover the other one. So for this talk, I've chosen to just look at the ones that have edge length 1. But you're right, this blue thing is like not depicted in that space. Yeah. Are there other questions? Okay, so what we're gonna do is record this the combinatorics of this stratification in something called a dual complex. So the dual complex is associated to the compactification. So that's why I'm writing like delta of M0n inside of M0n bar. And this is going to be a simplicial complex where the vertices correspond to the irreducible components of the boundary, and the edges correspond to pairwise intersections of components. And then you get a triangle whenever you have a 3-way intersection, and so on. So I'll say what it is for this example, but since there's no, the red, the green, and the yellow don't intersect each other, there's not going to be something super interesting going on, but I'll give you like another example as well. So
uh,
here we
just
have, yeah,
one question.
yeah.
So when you say triangle and so on, does that mean it's a complete graph or it's a cycle?
It's gonna be, so this is it's building a simplicial complex. So to get
Okay.
simplices of
Oh,
like,
so
if you
it's
wanted like a simplex of higher dimension, then you would have like something
okay,
with
okay.
more intersections, yeah. Um, yeah, so in this example, we just have these 3 boundary components and they don't intersect each other. So that just gives me the dual complex is just 3 points. So not super complicated. So I'm going to give you another example where there's a little bit more going on. So if I want to compactify C star squared by P2, then what have I added in? So let's say my coordinates for P2 are going to be x0, x1, x2, like that. Then when any of those is 0, that's something that I've added in my boundary. So I have these 3 components. So I have the one where x0 is 0, x2 is 0, and x1 is 0. And then those each intersect in a point where 2 of the coordinates are 0. Okay, so the dual complex, I'd get one green vertex corresponding to this green component, one red vertex, one yellow vertex, and then they each intersect pairwise, so I get an edge between them. But the triangle is not filled in because the 3 components don't all intersect. So that's like an example where there's a little bit more going on. Okay, so you might have noticed from this first example that this dual complex is actually the same thing as the tropical moduli space that we constructed before. So this is sort of like an overarching principle. So often the 2 spaces are equal to each other. So if you have the boundary complex of some compactification and you compare that to the like synthetic combinatorial moduli space, so you like cook up a moduli space consisting of some combinatorial objects, often those 2 spaces are the same as each other. And there's a lot of examples of this. So MGN, which is N-marked genus G curves. So this was shown by Abramovich, Caparasso, and Payne in 2015. There's also like a moduli space of admissible covers where these 2 spaces equal each other, and that was proved by Cavalieri, Markwig, and Raghunathan in 2016. And you can also do this for the moduli space of abelian varieties, which was done by Chan, Mello, and Viviani in 2013. And there's more examples. I think these are sort of like the keystone like main examples. Okay, so like what is this actually accomplishing for us? So we have this like nice duality go between algebraic geometry and combinatorics. But what can we actually do with this connection? So it turns out that a piece of the cohomology of a moduli space can actually be computed from the tropical moduli space. So this takes an algebraic geometry problem, which is understanding the cohomology of a moduli space, which is a very hard problem. Like mathematicians have been trying to understand the cohomology of the moduli space of curves for a long time, and there's definitely there's a lot of results in that direction, but there's still many questions. So it takes this problem and converts it into a combinatorial one, which is computing the cohomology of a simplicial complex. And this is something that's a lot simpler to do. Like if you have a good description of your simplicial complex, then it's something that like your computer can just compute. So so this is really exciting because it takes something that's like very abstract and complicated and turns it into a combinatorial question that's pretty like computational and concrete. So here's like the sort of theory behind how this works. So there's like a theorem of Deligne that makes this all go. So I'm gonna let X now just be a complex variety. And Deligne gives a canonical weight filtration on its cohomology. So if I look at the rational cohomology of my complex variety, there's a canonical way to break this up into some subspaces. And this W0 one is the one that combinatorics will be able to say something about. So if I have a normal crossings compactification of my complex variety, so meaning that the boundary components that you add in all intersect each other transversely, then there's a theorem of Deligne that says that W0 piece, so this blue piece right here of the cohomology, that is actually given to you by the cohomology of the dual complex of your compactification. So what we were doing a few slides ago, where you write down a simplicial complex that recalls the combinatorics of how the boundary strata intersect each other. So I think the take-home message of this theorem is like if I want to compute a piece of the cohomology, so this isn't going to give me everything, but it'll give me something. If I want to compute a piece of the cohomology, then it's good enough to look at this tropical space. So here's like an example. So let's go back to M0n. So by the theorem, if I want to say something about the cohomology of M0n, then I can just look at this tropical moduli space. And this space is actually, it's been studied for a long time because it's also the space of phylogenetic trees. And so Voigtman proved in the 90s that M0n trop is homotopy equivalent to a wedge sum of n-2 factorial spheres of dimension n-4. So using that information, then you can apply Deline's theorem and compute something about the cohomology. So this is like what Deline tells us in this instance. Okay, and then there's a lot of recent results using this idea. So the first main one was the looking at the top weight cohomology of MG, so the moduli space of curves, and Chan-Galicius and Payne proved that there was some non-zero cohomology for G 3, 5, and greater than or equal to 7. And then they also did a computation that gave the formula for the SN equivariant Euler characteristic of the top weight cohomology of MGN. So these were sort of like the first two results in this direction where you use these tropical techniques to try and say something about the cohomology of a moduli space. And then since then, there's been more work done, in particular with a group of co-authors. We computed something about the top weight cohomology of the moduli space of abelian varieties. So we were able to compute it for a few values. This is sort of like an abbreviated list of papers at this point because people have done a lot more with these ideas. But yeah, so I guess the take-home message here is like there's been a lot of recent activity in looking at tropical moduli spaces and trying to use them to compute something about the corresponding classical moduli space. Maybe I'll pause here if there's questions.
Not a question per se, but what's up with the numbers? Are you the numbers in the cases? Is there like anything you can say about that?
Oh, here, these pink ones? Or is
Yeah.
Yeah, so there was an open question of Grushevsky, which was like, is there ever odd cohomology for AG? And so this answers that question and says that yes, there is. In these cases, there's some odd cohomology. Yeah, which
That's
is
cool.
like, yeah. So like the significance is like the classical sort of like algebraic geometry techniques for that we have for getting at the cohomology often only give you even degree cohomology. So yeah, that's like why that question exists. But yeah, thanks for
Nice.
that.
Yeah,
Do you,
and sorry, no, go ahead.
no. Oh, okay.
I
I
was
was
just
gonna
go ahead.
okay, I was gonna ask if you expect odd cohomology for only odd genus or higher
Oh,
genus cases also for even G.
yeah, that I don't know. Yeah, so this like computation was done very explicitly. Like people had already computed the tropical, like AG trop, up to some G, which is larger than 7, but the number of simplices in your simplicial complex just like explodes. And so since we were like more or less doing these computations by hand from like what was known, it becomes like hard to do it after G equals 7. And so I don't know, but I don't think there's any reason to expect that it would only happen in odd genus. Yeah. But yeah, for now, this is like sort of what we know. Was there another question or
That pretty much answers my question. I was gonna ask how do you generate those numbers, but yeah.
yeah. Okay, so I'll continue on. So that was sort of like the overview of like what is the technique and what are people doing with it. And so the next thing that I was gonna talk about was a case where with Melody Chan and Siddarth Kannan, we tried to compute something about the moduli space of hyperelliptic curves. So I'm gonna let HGN denote the moduli space of n-marked hyperelliptic curves of genus G, which I'll define that on the next slide. And there's some previous results about the weight zero cohomology. So in Tomasi's thesis, it was proved there are a few results along these lines. And then there's also a paper of Bergstrom in 2009, which computes the SN equivariant Euler characteristic for all G, but n less than or equal to 9. And yeah, I didn't say what this is either, but I will say that later because that's like also the thing that we're trying to compute. Okay, so what is a hyperelliptic curve? So I think the easiest definition is just, you could say that this is a curve, a plane curve defined by an equation, y squared equals f of x. And then there's like two more sort of like abstract definitions. So the first one is that this is a curve that has an involution, and when you quotient out by the involution, you get P1. So for this guy, if you have a curve presented to you in this form, you can get the involution by just taking a point on the curve xy and multiplying the y coordinate by -1, and that gives you your involution. And then the third definition is that this is like maybe the more typical definition if you're an algebraic geometer, but you would say that this is a branched double cover of P1. So this is like my cartoon of how that would look. So here's like my branched double cover, and then downstairs I have a P1. And okay, so how do you go between all of these definitions? So if you start with a curve with an involution, then the fixed points of the involution are your branched points in this double cover. And the quotient is the double cover. And then to go between these two, if you look at the roots of your polynomial, those are going to give you the branched points of the double cover. So these are sort of like three perspectives that you could take to look at like the question of what is a hyperelliptic curve. And in this talk, like this sort of cartoon is like the thing that will come up the most. But yeah, like crucially, looking at this cover downstairs, we have like a P1 with some special points marked. And those, you can think of those as just being like the roots of your polynomial f. So like where are the branch points of this double cover? Okay, so let's look at, for now, just HG. So I'm just looking at hyperelliptic curves that don't necessarily have an n marking on them. So no marked points, but just an HG. So a choice of 2G plus 2 branch points on a P1, by what we were saying on the previous slide, this gives you a genus G hyperelliptic curve. And the 2G plus 2, this is just like a Riemann-Hurwitz calculation. So it's like a Riemann-Hurwitz is just sort of like a standard theorem in algebraic geometry that you can use to calculate like the genus of like a cover given some information about the branching. So, but anyways, if you do that calculation, if you want a genus G hyperelliptic curve, then you need 2G plus 2 branch points. Okay, so if I pick out my 2G plus 2 branch points on P1, by say selecting a point in M0 2G plus 2, so like M0N, where N is now 2G plus 2. So that's pretty good, but the points come with an ordering in M0N. So then what I want to do is just mod out by the symmetric group action that permutes the labels on the points, which will just forget the labeling. So that is like what the moduli space HG looks like. And then if you compactify this and look at the boundary complex, it is exactly M0 2G plus 2 trop modded out by S2G plus 2, which is actually a contractible space. So what we get in this example is that the weight 0 cohomology is 0 for all I and G. And that's actually consistent with like the results from 2 slides ago from Tomasi. So that's just like, I guess, an example of like running this technique in like the first case where we have 0 marked points. Are there questions? Okay, so wait, also, by the way, am I supposed to stop after 50 minutes for questions?
You can go a little bit more if you like. We have till 2, so if you have a few more minutes, but yeah.
Okay, I'll just do the rest of this in brief. So if we want to use Deligne's correspondence theorem, we need to construct this guy. And what we need is a normal crossings compactification of HGN, which is like maybe one of the more challenging steps of this process. And then we also need an explicit description of this boundary complex. So I'm going to skip this because it's like a little bit heavy in the algebraic geometry and we're short on time. So let me just let me skip to the picture. Okay, so what are these? These are tropical double covers. Sorry, okay, so this upstairs we have a genus 2 tropical curve. And it's 1 marked. So I have like one little leaf labeled 1 somewhere on the tropical curve. And it is a double cover of a tree. Okay, so what I'm doing is constructing a moduli space of all such things. And so let's go down all the way down here to the vertices. So the vertices are going to correspond to the ones that have where the tree has 1 internal edge. And so you can see there's like 3 sort of different types of covers. And then when you have 2 internal edges, those give you the edges of your tropical moduli space. And then we have the triangles and the tetrahedra all the way upstairs. So this is like on the tropical side, the types of objects that we're looking at. And these are like dual to the types of curves that appear in the boundary of our compactification of HGN. So like this was something that would have appeared sitting in the boundary of the compactification of HGN, and this is the corresponding tropical double cover. Okay, so then we computed something called the SN equivariant Euler characteristic of HGN. So yeah, I'll just say like how to think about this. So it's sort of like a generating function for all n simultaneously of an Euler characteristic of something called the Frobenius characteristic. So so like the cohomology is at the end of the day just a vector space, and there's an Sn action on that vector space, which permutes the marked points on your curve, and that Sn action is compatible with the cohomology and the taking the weight zero part. And so you can think of this thing as an Sn representation. And what this does is it just records that Sn representation as a symmetric function, because symmetric functions have a basis corresponding to partitions lambda of n. So anyway, so we're taking like some symmetric functions that remember what representation this is, and then we're like adding them all up. And then this is our theorem. So basically, I'm not going to get too into the details, but what the theorem says is that I can look at a finite sum of trees and then do some computation, and that will give me this Sn equivariant Euler characteristic. And doing that, we're able to, there's an example. But anyway, so doing that, we're able to get like an explicit computation done for G up to 7 of like what this weight zero compactly supported Euler characteristic is. And you can actually recover the ordinary numerical weight zero Euler characteristic from this. So that's like what the table is. But anyways, sorry I sort of like rushed everything at the end, but it's because we were like, I think it was worth it because the first half of the talk is like more important, I think, for just like getting a general sense of like what is going on. But yeah, thanks for your attention.
Thank you so much, Maddie, for a wonderful talk. Yeah, we'll open it up for questions. Are there any questions?
I have a very naive question.
Yeah.
So, like, why do we care about studying n-marked P1s or like n-marked curves in general? Like, why is that an object that people are interested in studying? As someone with like no AG background.
I think like one thing is that like it sort of comes up very naturally. So like, for example, like even just looking at hyperelliptic curves, like what we saw was that looking at a hyperelliptic curve is equivalent to selecting points on a P1. So like, and yeah, there's other ways in which it comes up very naturally. Like, so yeah, if you start like trying to define like morphisms between curves or between moduli spaces, often you need to make like some selection of points. And so yeah, like being able to handle marked points ends up being like a necessity, basically.
I see. Okay. That makes sense. Thank you.
I'm wondering, in the computation of little hg, it was a finite sum over trees. How does this number of trees grow
Oh, that's a good
in G?
question. I actually don't know the answer to that. So okay, well, there's one ingredient that I don't know, which is like that I probably should know, which is like how fast does the number of trees with a fixed number of leaves like grow in general. But also like we can toss out a lot of them, so it's like a little bit better than that, but maybe not actually better than that. So okay, so in short, I don't know the answer to your question, but it is like it grows fast enough that doing like I was only able to do G up to 7 on my laptop.
Oh, okay.
Yeah. That's why it stops at 7, is because I was like, okay, this is like enough. Yeah.
Any other questions? If not, let's thank Maddie again. Go ahead and stop the recording.